So to answer question 1, we need our standard geodesic equation. Since the vector xu has got 4 components, we'll end up with 4 geodesic equations, and thus we will have to use our general geodesic equations for each component, namely t, theta, r, and phi. So if we look at the time geodesic just as a reference point for us, our standard geodesic equation becomes, whereby we've used this specific Christoffel symbol because it's the only one present in the question. Now, to determine the differentials next to the Christoffel symbol, we have to look at the values of sigma and pi, which are given by the subscripts of the Christoffel symbol. In this particular occasion, notice that sigma is not equal to pi. This means we'll have to include a factor of 2 into our geodesic equation where the Christoffel symbol is. The reason for this is because sigma is not equal to pi, which means our Christoffel symbol is not symmetric, it's anti-symmetric. So we have to account for a sigma p Christoffel symbol and a p sigma Christoffel symbol, meaning that the 2 indices can be swapped around, giving a rise to that factor of 2. A similar process continues with the other geodesic equations, but for instance, our radial geodesic equation contains all symmetric Christoffel symbols, so we don't have to include this factor of 2. We use a similar process for the other 2 equations, subbing in the values for the Christoffel symbols. For the other 3 geodesic equations, we have more than one non-vanishing Christoffel term, so we have to add in these extra bits into the geodesic equation. These geodesics are significant because they give us a more concrete, comprehensive, and more accurate understanding of the way things move in space. One of the ways this is noticeable is in the precession of the perihelion of Mercury. Newtonian mechanics doesn't yield a precession that is as large as the precession observed. However, applying the geodesic equations to Mercury to understand its motions do. So question 3 asks us to look at the radial geodesic equation. And from pi being set to a constant, and from understanding that a circular orbit will mean the radius is also constant, we can remove all the terms involving a differential of r and theta. Simplifies our equation quite a lot.
Yeah, baby! That's what I've been waiting for!
From this, we simply have to rearrange our equation as well as KFC, whereby we get a value for d phi over dt squared. Now, to relate this to Kepler's third law, we have to understand that d phi over dt is merely a way to describe the angular velocity, denoted by w. And we also know that w is related to the time period, therefore we can sub in omega, then rewrite that omega in terms of t, which leaves us with the relationship of Kepler's third law.